I'd like to thank the organizers for the invitation, and also I'd like to thank the organizing this great workshop. So I'd like to talk about the undulation phenomena in smectic liquid crystals, and this is a joint work with Carlos Garces Rivera at UC Santa Barbara. So first I will just talk about some introduction to the liquid crystals and the model that we are going to use and what causes the undulation in smectic liquid crystals, and the method that we use to study this functional. We use the gamma convergence theory, it's easy case, and bifurcation and stability analysis, and we do these numerical simulations to confirm the prediction of the analysis, and we extend our theories and simulation to the Chen-Lubansky model. And finally, I will just talk about some work done on the undulation in three-dimensional domain. So we've seen this picture several times already now. So this liquid crystal phase is between the solid and the isotropic phase. So I'm just going to talk about these collimated liquid crystals, which composed of the elongated rod-like molecules, and because of this shape of the molecules, so we can have this liquid crystal phase. So this is a solid and an isotropic phase, and this is N is the preferred molecular orientation, and it's denoted by a unit vector. And I'm more interested in the smectic phase. So in the pneumatic phase, it only has the orientation order, but in the smectic phases, we have the positional orders. And there are popular two types of the smectic phases. In the smectic A phase, the molecules are perpendicular to the layers, but in the smectic C phase, there is a tilt angle between the layer normer and the directors. And I'm interested in this response to the applied field for the smectic phases. And if you apply this magnetic field in this direction with the positive diamagnetic anisotropy, then molecules will follow the direction of the applied field. Then in order to change the direction of the molecules, you will have to disturb the layer structure, and that causes, and with the fixed boundaries top and bottom, so that causes the undulation in the smectic A liquid crystals. But in smectic C liquid crystals, this is used as the device, and I'm not going to talk about much on the smectic C phases, but you can imagine the three-dimensional space, and in order to have this, as long as you have this tilt angle between the director and the layer normer, it's going to be a ground state. So if you apply this electric field, you don't have to disturb the layers. It can just switches to the other side of this the surface of the cones. This is the Austen-Frank energy, and this is a splay deformation, twist deformation, and band deformation, and these are the configurations for this. So if you, for example, if you have an R theta and Z coordinate, if you put that, then only the first term will be non-vanishing and the other will be zero. So that's responsible for this pure splay deformation, twist deformation, and band deformation. The last one is the non-Lagrangian. That means it's going to be the integral over the surface of the domain, and we only talk about this. We're going to talk about this on one constant approximation. That's going to be a simple rod n squared. And I'm just showing this picture for the colastic liquid crystals because I believe this experimental work done on undulation phenomena, I believe they use this colastic liquid crystals instead of smectic materials, because so by putting this tau into this twist deformation, this becomes non-zero. So that's going to be a twist favors the twist deformation. So this is the picture for the colastic liquid crystals, and you can understand that this is the half pitch. So if you just twist around that, but every half pitch, you can view that as the layers. So this can be viewed as a lamellar system, and I believe experimentally they use this material probably because this thickness or the half pitch is like in the micrometer range, but in the smectic liquid crystals, this layer thickness is the nanometer range, so it's going to be harder to visualize. In order to describe the layer structure, we're going to need another parameter variable. So this is a complex order parameter that introduced by the Zhen in the line of analogy between the superconductivity and the smectic liquid crystals. Okay, so this is if the psi becomes 0, then the mass density becomes uniform everywhere. So that means we're going to lose the layer structure. So that corresponds to the nematic phase. For psi is that's why the psi becomes the order parameter, and that phase parameterizes the layer structure so that the grad phi becomes the direction of the layer normal. So we are going to need these two parameters, so director and the complex order parameter psi, to describe the smectic liquid crystals. So we are going to add them together. So this is the simplest possible smectic A energy, and you can see that if the phi is the phase, then this grad phi wants to be parallel to n. That is exactly describes the smectic A energy, A phase. And as usual, this is going to be phase transition terms, so that penalizes the phase transition. So this is just a picture for the undulation. If you apply this magnetic field in this direction, so right now it's a flat layers, so the molecule directors are going to be in the vertically aligned like that. But if your magnetic field is not strong enough, then you cannot disturb the layers, so nothing changes. But if it is above the threshold, then you're going to have some undulations like that. This is called the Helfrich-Raute effect, or undulations in smectic liquid crystals. So this is the picture done by the Lavrentovic in 2001. That's a two-dimensional picture, and they also did the three-dimensional experimental work in 2006. So I'm just talk about this conventional theory, the traditional Helfrich-Raute theory. So they use this small displacement, and also they identify this director and the layer normal direction and use the strong anchoring condition. So this is going to be the free energy that they used. So only one parameter there, and then they also made an ansatz and look for a solution of only this type, and then minimize it, then find the critical field and undulation mode for this energy. And this is the classical Helfrich-Raute theory, but this is the experiment done by Lavrentovic at Kent State University. And there is the discrepancies between the experiment and the Helfrich-Raute theory. The major differences are the following. So actually the critical field is lower than the found in the classic theory, and a larger layered displacement, and displacement of layers near the boundary, top and bottom, is not zero. And of course, because of that, so we have a weakened dependence on the vertical coordinate for this undulation displacement. So we want to explain these things to kind of confirm this experiment. The Lavrentovic actually did some of the proposed this model, instead of the strong anchoring condition, he used the weak anchoring condition. So that means he included the Rapini-Popolo surface energy. So instead of the usual boundary condition on the director, so he used this the Neumann boundary condition there, and so with that model, and he identifies the director and the grad phi, the director layer normal over the modulus of that, and weak anchoring condition, this is the weak surface energy, and also they made an ansatz to look for a solution of this type, and this model explains the experimental data a lot better than the previous one. So let me go back to my free energy. So this is the June free energy. So this is a smectic A, the complex order parameter, and this the nematic energy and the phase transition terms, and this is the magnetic energy. So we are in this two-dimensional rectangular domain, and this is undeformed state, and for 2D, we are using this angular variable, and we have this second-order variation. Then we can have we can define this critical field by this second order variation of the free energy, and basically we want to find this critical field and the solution at the critical field. So in order to kind of follow this physical interpretation, so we use the periodic boundary condition on the lateral side, and we use a strong anchoring condition for the director. But for the layers, we use two different types of the boundary conditions. First, we fix the layers at the top and bottom as well. But the second type, we kind of look for the general case. So the layers are going to we enforce this natural boundary condition on the layers. So this kind of follows Hong and Pan's work. So we put this transform our psi into this, then this linearized energy becomes like that. So this is part the imaginary of the phi. Then if this becomes 0, then we are going to have the lower energy. So we are going to assume that this phi is a real valued function. And we do this non-dimensionalize the energy, and while we are doing this, this domain, it becomes like a unit rectangular domain, and but we were able to capture this small parameter epsilon. This is a ratio of the layer thickness to the cell thickness. So this is a very small parameter. In smectic A, it's like a 10 to the minus 5. In a cholesteric crystal, this I believe this experimentally theirs was like a 1/10. So this is a small parameter, and the first approach that we did was to estimate this critical field. We found this, we proved this lower bound and construct the upper bound for this energy. So we know that this critical field is order 1, but actually we can what we do is this periodic boundary condition, this becomes this one-dimensional free energy, and so this is the energy for that, and the delta is the parameter, the variable as well now, and we prove that this minimizer is either positive or negative in this domain. So that means we can restrict ourselves in this space. So the first one is the natural boundary condition on the layers, and that one is a dirichlet boundary condition on the layers, and we look for a minimizer of that with this constraint. So we use this first we use the gamma convergence theory to understand the minimizer of this functional with epsilon. The nice thing about this gamma convergence, usually if you have this epsilon to functional, then people are trying to find the Euler-Lagrange equation and then find the limiting behavior of this solution. And for the gamma convergence theory, we prove that this gamma converges, the functional gamma converges to the gamma limit F naught. Then what's nice thing about this is that minimizer of this sequence also converges to the minimizer of the gamma limit. But of course, just roughly speaking, it's not exactly the sequence itself converges to that, but with this compactness result, every cluster point of this minimizer is a minimizer of this gamma limit. So in order to prove this, we need two inequalities. First, the lower bound inequality. So that means whatever sequence you choose to approximate u, then this limit, this function value in the limit has to be larger than f of u. And this upper bound says this inequality has to be sharp. So this is the with these two inequalities. It also always should be paired with this compactness result. So people try to prove these three things to use this gamma convergence theory. And if you can prove this, and then this minimizing sequence admits a subsequent approximating solution of the problem of the minimum of the gamma limit. So first we'll have to construct our gamma limit, and we prove the fixed layers case. This is an easy case, kind of two case. So if you just the gamma convergence theory for this, then this is our gamma limit, and for this fixed layer case, it is very easy to see that. And the gamma limit has and we proved that gamma limit has the unique minimizer. That's why we restricted ourselves into that kind of a restricted set for either only the positive solutions, because the gamma limit, when the gamma limit has a unique minimizer, then the sequence of the minimizer itself converges to the minimizer, that unique minimizer of the gamma limit, not only the subsequence. So we can prove that this our minimizer can be approximated by the solution, the minimizer of the gamma limit. So this is a result on that. So we can have this, we can approximate our minimizer by the minimizer of the gamma limit. And what we have is we have this frequency of the oscillation. We can have the critical field, and we can see that this is the phi is approximated by the cosine function in the vertically. So that means we have the maximum undulation in the middle of the cell, and it have 0 at the top and the bottom. So decreases undulation amplitude decreases as it approaches to the top and bottom of the cell. That's exactly the same result found in the classic Helfrich-Schwarz theory. So that's what we already expected, because we are fixing the layers on the top and bottom. But we are more interested in the next case. So layers are not fixed anymore. So we use the natural boundary condition on the layers. So this, in this case, phi does not have to be 0 now. So it's kind of clear what we expected if you look at this functional. So theta wants to be equal to phi, but with this constraint, the delta has to be small. Then 1 over delta is big, so phi prime has to be 0, wants to be 0, so phi wants to be constant. But theta cannot be a constant because theta is 0 at the boundary and with this constraint. So only way to satisfy all those things is when we have the boundary layers on theta. So this is not the solution of this because we already I already set these values for the delta. Delta is unknown, but this is just a picture that because we just wanted to try to understand. So we have this gamma convergence theory again. So this is the gamma limit. The only difference here is the boundary values there. So if you have with these boundary values, then we can connect the weak anchoring condition for the kind of surface energy that Lavrantovic included. So if you go back to, I don't know how to do that. So if you go back to this energy, so then okay, so Lavrantovic, he used this weak surface energy there, but if you linearize it, then if you linearize this surface energy, then this is exactly what you have in the gamma limit here. So this is the connection between this weak anchoring condition of the director and the gamma limit that we have in the natural boundary condition on the layers. So once you prove this gamma convergence theory, proving this is a little bit harder than the previous case because we have the this is similar to the Lacan, but we have the boundary conditions on that, so we have to consider the Dirichlet boundary condition for this. And after that, once you prove this, then we have this unique minimizer. This is just constant, and the minimum value of this free gamma limit is a lot smaller than previous one that was pi previously, but now it is 1. So we just decreased our critical field. And again, since it has the unique minimizer, sequence of the minimizer itself converges to the minimizer of the gamma limit. So again, we can approximate our minimizer by the minimizer of the gamma limit then. So this is, you can see that this vertically, it does not depend on this y values, it's just constant. So we have weakened dependence on the vertical coordinate, and we have this critical field. Of course, we have these undulations near the boundaries. So these can explain, of course, the larger, because of this, we have the larger undulation displacement. So that explains that experiment done by Lavrentovic. So in order to connect this nonlinear problem, we use the bifurcation theory, and so this is the Euler-Lagrange equation for the complex energy, and we have we prove that this has this simple eigenvalue, and we use the Crandall-Rabinovich theory to prove that it is a simple eigen. This is a bifurcation point, and this non-trivial solution becomes stable. So this is the energy. The linearized problem, and we prove that this is spanned by the one element. So corner is one-dimensional in the except discrete set of the domain sizes, and for the Dirichlet boundary condition, and we can see that it kind of matches the result we found in the gamma convergence theory. And for the natural boundary condition, again, it is not straightforward to find this the solution of this corner. So what we do is we use the asymptotic estimate to find this corner, and we use the result from the gamma convergence theory to make it simple. So after that, once you find this the eigenfunctions, then this is the graph of the eigenfunction, and when epsilon is 0.1, you have a little bit of differences between the theta and the phi, but it's going to be getting same with having this boundary layers on theta there. So that's what we expected in the previous picture as well. So again, using this theories, bifurcation theories, we prove that this critical field, that is a bifurcation point, and we have this non-trivial solution curve becomes stable after the critical field. And this is the supercritical pitchfork type of the bifurcation. We kind of expected that because the positive solution and negative solutions are the same minimizers. So this is now I want to talk about this numerical simulations that we did. So this appears because of the constraint on this unit director, and this is the same as having the Lagrange multiplier, and we have this gradient flow of this Lagrange system, and we applying these two different boundary conditions on the layers. So in our analysis, we predicted our critical field. Critical field has to be like a pi over h after the scaling again. So pi over h is going to be 0.252, and in the numerically what we see is at 0.25 we do not have any layer undulations, but at 0.255 we start to see these undulations. So that means we have a good agreement between these numerical simulations and the analysis that we used, and we have a little bit bigger undulations after that. And for the general case, if you apply this the natural boundary condition on the layers, we expect to have a lot lower critical field and the bigger undulations. So this is what we had here. So again, good agreement between this the analysis we had and this numerical simulations. A lot big undulations now. But that was, the previous one, we used this constant layer density, but of course we can use this non-constant layer density. So this is the dimensionless free energy now. We dimensionalize this free energy, and again, this is the gradient flow equations, and then we can have some phenomena well above the critical field. So this is the experiment. So two-dimensional experiment, the vertical dependence of the layer undulation is negligible except near the boundaries, and actually near the boundaries they expect to have some kind of boundary, join the boundary discontinuously and form array of dislocations. So this is what we have. So you can see that in the fixed layers case, this becomes a lot sharper and sharper, but at the boundaries, you see that this is kind of joined discontinuously there. But in the general case, on the other hand, it's just at the near the boundaries, the directors and the layers, they just decouples completely. So this is the in order to see more clearly, this is a contour map of this dimensionless layer density psi squared. So the blue color corresponds to the 0. So that's where this smectic phase melts, or like a vortex in the superconductivity. So this is the moderate field and at the higher field. And for this, if you fix the layers on the boundaries, then you can see that all this 0, kind of the smectic phases melts around this the boundaries. Yes?
What is the layer in the picture?
This is the contour map of this psi squared. And in this general case, you can see that at sigma equals 1, we already see lots of the smectic melting occurs there. But at sigma equals 1.5, in the general case, you don't see any of this here. So at a lot higher field, you will have this kind of smectic melting occurs in the middle of the cell. So this is the differences between this fixed layer case and the natural boundary case on the layers. Now we extend this to the Chen-Lubansky energy. So the Chen-Lubansky energy was proposed in 1970s, and the Lukashchuk is it's modified in 1998. So that is kind of a effort to understand the smectic A and the smectic C. So this is the picture for the smectic C star. So this, you can see that this is the molecules are around the surface of the cone. Then you can just move around for the chiral molecules. So we can assume that we are going to assume that psi is away. We are assuming that we are away from the phase transition. So constant smectic density, layer density, and this is going to be the fourth order differential equation. The Euler-Lagrange equation will be the fourth order differential equation because of the Laplacian in the free energy. So if whether you have this positive sign or negative sign on the C perp, you can have this smectic A energy or the smectic C energy. So this, but again, I'm just going to talk about the smectic A energy for now. So dimensionless free energy is like this, and we can do the same thing as we did before. So we can extend our gamma convergence theory and bifurcation analysis on this. So I'm gonna skip that. What I want to say is that numerical formulation for the Chen-Lubansky model. So in order to solve this fourth order differential equation, instead of that, we are going to reformulate this down to reduce this to the second order differential equation with this constraint. So instead of having this, we take this U equals grad phi, then this energy becomes only have this first order gradient, and this corresponding Euler-Lagrange equation or gradient flow equation will have only the second order. With this constraint, this becomes just the Laplace of U. So we have this nice equations, but of course we have this constraint. But this constraint, instead of this constraint, we have this Lagrange multiplier. So this is the pressure. It's like the pressure in the Navier-Stokes equation. So instead of solving the fourth order differential equation, we are going to solve this Navier-Stokes kind of the Navier-Stokes equation, because there are lots of ways, not lots maybe, but there are ways to solve the Navier-Stokes equation. So we're going to use and we use the gauge method proposed by Wainanin and Liu in 2003. So we used this gauge method to solve that for the Navier-Stokes equation. What's nice about this is usually the Navier-Stokes equation, what I understand is that in order to solve this Euler equation, the Poisson equation for the pressure, it has the boundary conditions. So in order to avoid this, people use the projection method or this gauge method. So what's nice about gauge method for me is that we can just solve this equation like this standard heat and Poisson equations. So this is the equation that the method that we used, and after that, once you solve the equation, find the u, then you can recover your layers by solving this equation again, because grad phi equals u, and with this appropriate boundary condition, you can solve this equation. Then you can recover your layer structure. It's like a stream function in the fluid dynamics. So with this gauge method, we solve this these equations, gradient flow equations. And this approach is generally works very efficiently for this type of dysfunctional. And first, we use the Avar-Giga functional with the perpendicular anchoring. This is the Avar-Giga functional with this type of the functional, and that works very well. So we have this perpendicular anchoring, and that's what we had. And so we are using this method to our case in the smectic A. Again, this is the divisional boundary condition. Then you can see that at 0.27 we have the undulation. So this critical field matches again, and that's what we are going to have. The second picture is just the toy problem in the smectic C. I understand that it has to be the three-dimensional domain, but we are using this two-dimensional rectangular domain. So if you use this homogeneous boundary conditions then you are not going to have any undulations. So we just have this the boundary conditions, and it's fixed like that. And the other is the negative tilt angle. Then at some point you'll see some undulations, but I don't think there is any physical meaning behind that. So to confirm our numerical simulation, we did the asymptotic analysis of this problem. Again, this may not be physical because we are using this constant layer density case. So when psi becomes big, the strength of the magnetic field becomes big, then you are going to have some phase transition. So, but it just gives a nice consistency between the numerical simulation and this approximation. So we use the asymptotic analysis in this case, and this is the graph. This is a graph using this asymptotic analysis, and this is a graph from the numerical simulation, and they have a good agreement. Finally, this is a three-dimensional linearized three-dimensional space. In order to study this three-dimensional undulations, we apply this magnetic field in the vertical direction with this negative diamagnetic anisotropy. So that means this molecules prefers to be perpendicular to the applied field. So by omitting this constant terms, you can see that this is going to be the magnetic field. So it follows this, wants to be x or y direction. So with this non-dimensionalized energy again, then we can, instead of using the angular variable, because we are in 3D, we use this definition of the critical magnetic field in the Lin-Pan or the previously and by Luskin, and we can find this critical field, there, and with some work we can find we were able to have the estimate for the critical field for both cases. And this is the picture simulations that we did for the three-dimensional numerical simulations. So in the traditional boundary condition, first you have a 2D square lattice of undulations with this vertically applied magnetic field, and you can see that undulation period increases with the strength of the field. So that's what we expected in the experiment, and this is the director configuration. But when it's well above the critical field, Lavrentovic group, they expected to have the 1D pattern bounded by the parabolic whir, but that starts that is kind of start with this axially symmetric domain like this. So we do not have the parabolic whir yet, but we have the similar to this axially symmetric domain. So we first near this critical field. So this is a square lattice, 2D square lattice. So this is the XZ phase, and this is a YZ phase. So you have this exactly same type of the undulation. That means that you have the 2D square lattice, but in this higher field, you have this is the YZ phase. So this is a very weak undulations at the higher field, but we have the very strong undulation like this type on the XZ phase. So this is the and also we have this layers. The natural boundary condition. The layers near the critical field. First, we don't have any undulations. This is the undulation. This is the undulation in the middle of the cell, and we have a little bit of that and more. And what see is after we're above the critical field, this two-dimensional 2D square lattice just becomes transforms to the 1D stripe pattern, and that's what we had in the natural boundary conditions. So in one direction you do not have any undulations, and the other direction you have these strong undulations. So let me conclude my work. The Dugin model, we use the Dugin model with the natural boundary conditions on the order parameter with this strong anchoring condition, but the natural boundary condition on the layers. So then it agrees with these experiments, the lower critical field, bigger undulations, weak dependence on the vertical coordinate, and we actually see the undulation near the boundary, and we do this bifurcation from the bifurcation analysis. So we say that there is a supercritical pitchfork bifurcated curve of a non-trivial solution above the critical magnetic field, and stability is the trivial solution is lost at the bifurcation point. And numerical simulation show that confirms the critical field and the undulation mode expected from the analysis, and we introduced a new formulation of the numerical simulation of the fourth order differential equations, and we have some work on the three-dimensional domains. Okay. Thank you.
So we have time for questions.